Alright, so let's take a look at our last worksheet for the unit, which is assigned as a grade. An engineer is testing a new crossbow to find the speed of the dart. The instant it's launched from the crossbow is fixed in a table. The dart is launched horizontally. The target is placed in front of the crossbow, so the crossbow is pointed directly at the center of the target. The distance d from the crossbow to the target is varied, and each time the crossbow is fired, the distance h from the center that the dart strikes the target is measured, so how much it falls. Got it. The data taken by the engineer are shown on the table. Part A. Using the assumption that the crossbow darts were projected horizontally, derive an expression for t in terms of h and g. Remember that the derivation should start with the fundamental equation of physics, an equation given on the AP Physics 1 equation sheet. I think we just kind of did this. If it's dropping, right, so we would have h. Okay, so we're going to derive it. H equals v naught t plus 1/2 gt squared, right? And this is 0. The initial velocity is 0. So h equals 1/2 gt squared. So multiply both sides by 2. And divide both sides by g. And step 5 would be t equals the square root of 2h over g. Just like on the last worksheet. Oh, I'm off the camera. That's unfortunate. H equals v naught t plus 1/2 gt squared. This is 0. Multiply both sides by 2 to get rid of the half. Divide both sides by g to get rid of the g. Take the square root of both sides to get t. There. I fixed it. Alright. Fill in the data table with the 5 values of t calculated using your expression from Part A. G equals 9.8 meters per second squared and a reasonable number of significant figures. Okay. So we need to go 2 times the square root of 2 times whatever h is divided by 9.8. And we're going to both say these are both negative so that the square root is positive. So I'm going to do it. 2 times 0.084 equals, divided by 9.8 equals square root 0.131. Feels like an adequate number of 2 divided by 9.8 is 0.204 times 0.169 square root 0.1856, round it. 2 divided by 9.8 times 0.408, square root it. 0.289, whoops, divided by 9.8 times 0.677, square root it. 0.372, 2 divided by 9.8, this is tedious, times 0.975, square root it. 0.446, okay, I got that part. Now what? Sketch the following graphs of the motion of the rock on the axis provided in the diagram of the rock. Light. That's all we're going to do with that? Is just fill in the data table? Okay. Oh. Sorry. No, we're not. It's actually over on this other piece of paper. 2D motion. It looks like there was a part 2 to projectile motion. I'm going to have to make another video for that. Okay, that was my bad. What quantities should be plotted on the graph if the graph is to have a linear trend and the slope of the best fit line is to be the launch speed of the dart? Whew. I don't know, man. You want me to just pull this out of the air? Oh my god. The launch speed of the dot is Vx. And the D is always the same. So, well, we have D. And we have equals Vx times 2h over g. That's the time. We calculated that. Right, we have the time. So Vx is equal to d over the square root of 2h over g. So what quantity should be plotted on the graph for a linear trend? Well, that's not going to give me a linear trend, is it? I guess I could say d divided by the square root of t would give me an inverse trend. Well, that would be so d equals v t, right? That would be on the x-axis, so d would be here. D would be here. That's the y. Y equals mx. And t would be here. And yeah, that's it, right? Y equals mx plus b, whatever that is. All right, so let's say that this is 1, 2, 3, 4, 5. And this is 0.1, 0.2, 0.3, 0.4, 0.5. I'm off the camera. Work hard. All right. So time, horizontal distance 5. This is 0.13. So this is 0.1248. So 0.13. This is 0.12, 0.14. So right here in the middle, right there. And at 10. Oops. 5, 10, hope you watched the whole video, 20, 25, okay, that goes here, my bad. At 10 we're at 0.186, so that would be right here. At 15 we're at 0.289, basically right here. At 20 we're at 0.37. 2, 4, 6, 8 right here. And then we're at 0.446 at 25, 0.446, it's basically right here. That does give us a pretty nice line, really. I mean, it's not perfect. And should it go through the origin at time 0? If the distance were 0, would it go 0? I don't know. I'm just going to draw the best line I can with what I've got and not worry about that. There we go. Label the axes. So this is d in meters. This is t in seconds. A scale. Got it. Units. Got it. Best fit line. Got it. Using best fit line. Determine the speed of the crossbow darts the second they have launched. Hint. Carefully calculate the slope and determine the relationship. Alright, so let's find the slope. So here's a place right here where I can find the slope. And where's another good place? Some place that crosses the graph paper is what I like. Here's one. I don't know if these numbers are going to be nice and easy peasy, but we're going to do the rise over the run. So here we are at 21, 22, 20, 22, minus, this is 1. And we're going to run, we're starting at 0.06. And we are ending up at 0.4. So that's our slope. 22 minus 1 equals 21. Wow, I used a calculator. Oh my god. This is taking too long. Not good. Times 21. 61.8 centimeters per second. Meters per second. Wow, that's pretty good. All right. That is 102D motion. 9 minutes. Yikes.